And then the most oxidized form of carbon, of course, is CO2. There's still no charge on the carbon compared to, say, methane, but this is, we consider this to be super highly reduced and this to be super highly oxidized, even though there's no charge on the one. It's just a little delta plus or delta minus.
So it's the same with nitrogen, basically counted the same as oxygen.
Yeah.
Nitrogen takes all.
Yeah. So the other thing we can notice here is that oxidation occurs together with taking away hydrogens. So dehydrogenation means remove hydrogens. And you can see that here, for example, the hydrogen to carbon ratio in methane is 4. The hydrogen to carbon ratio in carbon dioxide is 0. And as you go down this table, the hydrogen to carbon ratio goes down. So as you get more oxidized, you have less hydrogen hanging around. So that speaks to one of the key mechanisms by which the electron density, the electrons are actually removed. Okay. Any questions about this? Okay. Ways to transfer electrons. So if we're talking about redox reactions, we're talking about the transfer of electrons back and forth between compounds. There always has to be a donor and an acceptor. So how could we transfer them? These are the 4 ways that we can see that they're transferred in biological systems. So one is as a hydride ion. There's a pair of electrons here. Okay, and there are reactions that we will look at where there's hydride transfers, and that is a way of moving electrons around. We could imagine that they could be transferred directly as electrons. So there are going to be chains of electron transport that we will study that involve proteins, but on those proteins there'll be metal centers. And so the electrons can get moved between metal centers and oxidize and reduce the metals in the metal centers on the proteins. So that's another way to move electrons. Okay. We can move them as hydrogen atoms. Okay. So here we've got the donor molecule, which we're just symbolizing as AH2, and we're stripping away electrons and protons at the same time. Right? So this is perhaps the most common mechanism. This would be what we would think of as a 2-electron transfer. Right? We've got AH2, we're taking out 2 electrons, and we're taking out 2 protons. Right? And so this is also a dehydrogenation reaction because we're taking out the hydrogen. So this is, this is just written very schematically, but we will see specific examples of what this means. And then the last way is to actually directly combine with oxygen. So I think you can still see this. Here's an electron donor. Oxygen is the best electron acceptor in the cell. So when we burn fuel molecules with oxygen, we're moving electrons to the molecule that wants them more than anything else, more than any other molecule wants them that's around in the cell. So if we transfer directly to oxygen, and there are different kinds of enzyme classes that do this, and we'll encounter them later. There are oxidases, and then there are oxygenases. We don't need to worry about the distinction now, but it depends on some details of what the substrates and products look like. So here we've got a methyl combined with molecular oxygen, and we've generated an alcohol. Right? And so the oxygen has become reduced. Here it's the most oxidized, it's become reduced. The carbon has become oxidized because it's now bound to an oxygen. So this is a redox reaction, basically. It doesn't look like a conventional kind of redox reaction, but it's certainly a redox reaction for purposes of how we think about biochemical metabolism. Yeah?
And are these reactions balanced the same way as we learn in general chemistry?
Yeah, generally you can balance them the same way. We're not going to be balancing them, but yeah, you add protons and electrons and waters to the 2 sides in a defined order. Yeah, but we don't need to go there for purposes of this class. And I think you'll probably find as you look through the book that the textbook authors are not particularly rigorous about balancing them either. So here's our standard reduction potential table. Okay, so this is exactly like the table you would have learned about in freshman chemistry, except that it now includes a whole bunch of stuff that wasn't in the table before, but nonetheless still functions as redox reactions, right? So here's the standard reduction potential, E prime 0V, for a given half reaction, which is a measure of how much it wants to take electrons. So you notice that they're all written as reductions. This whole table is written as reductions. It's a reduction potential table. And yet, of course, when we're talking about a redox reaction, there's always a pair, right? If something's getting reduced and something else is getting oxidized, and then we want to predict what's the direction of spontaneous transfer. And when we do that, right, if we have one reaction up here, one reaction up here, the equation that we need to remember is delta G is minus NF delta E. So really this table of reduction potentials is exactly the same in principle as the thermodynamics of phosphoryl transfer, where we have delta G's going from ATP to ADP plus phosphate, or any other reaction. We have it's all thermodynamics in both cases. We have molecules of substrate here, and molecules of products here. There's a difference in delta G. Right? The only difference here is that we move from one to the other by transferring electrons, as opposed to, some more, reaction that the enzyme catalyzes, which of course also involves a redistribution of electron density in the molecules. It's just that here we think of it as a direct movement of the electrons. But it's still thermodynamics. We can measure it in terms of volts, but we convert the volts to delta G right away. Right? So this is nothing more than like your ATP free energy is minus 30, your phosphotriachin is minus 50. Here this reaction between this pair and this one is however it will come out based on the math of this table, which we'll look at an example of. Right? And the math of this table will give you a delta E, and then it's converted by the number of electrons, Faraday's constant, which is a conversion factor. Yeah, that gives you the free energy. Okay. So I'm sure that most of you, or all of you, have seen this table. Right? But I think it's good to recognize that when we have a table like this, it's a thermodynamics table, not a kinetics table. And it's the same kind of information as the delta G's that we're talking about just earlier today when we were writing them out for these phosphoryl transfer reactions and any other reaction you see. That delta G and this delta E are the same kind of thing. Right? So, if we're looking at bioenergetics in terms of what's going on with in glycolysis, this is what's going on in glycolysis. Actually, more than just glycolysis. This is what's going on in aerobic respiration in cells that live in oxygen-rich environments. They're burning their fuel, right? So let's say that their fuel is pure glucose, which you could dump into your car engine. It wouldn't work very well. It's not built for glucose, but there are engines that run on sugar as fuel instead of oil as fuel. And then, of course, we could write an equation like this for oil, which we will do because we're studying lipids as well. But let's write it for glucose, because that's going to be where we start with glycolysis. And we'll learn that glycolysis extracts this tiny little fraction, it's like minuscule little bitty bit, like 5% or something, of the total possible energy in the glucose molecule gets pulled out in glycolysis. Right, so this is the complete oxidation of glucose. Right, so this is a reduced energy-rich compound. Right. This is a highly oxidized compound. Here, this carbon has become oxidized. And the water is the reduced form of the oxygen, having also picked up a bunch of protons. this is reduced. So this is, thermodynamically downhill, and that's putting it mildly. Right, so obviously, huge amounts of energy that propel cellular life, at least heterotrophic life, by burning the glucose in the cell. And so this is going to be, energy is going to be extracted in a internal combustion engine burning oil or sugar or whatever it's burning. This reaction occurs all at once at conditions of high temperature and pressure. And a lot of the internal energy of the glucose molecule is wasted as heat. To the extent that we're smart engineers, we can couple that energy release to the movement of the car or whatever, but we're still wasting a lot of it. Whereas the cell wastes a lot less of it. And further, the energy is extracted in small pieces. So if the total amount of energy in there is something like 3,000 kilojoules per mole, and we want to extract the energy in pieces, what would be a good sized piece that you would want to extract the energy in? Like what number?
500.
500, you can only get 6 pieces if you got a total of 3,000. So that's a pretty big piece. You're probably going to waste a huge amount if you get a piece as big as 500. What number are we familiar with that would be a good piece that would correspond to what the cell is actually doing?
30?
30. So how about a piece that's, say, 30.5 kilojoules? How about a piece that's exactly that big? Right, because of course then we can do this. And so this will happen, as I mentioned, by substrate level phosphorylation, right, which we will see examples of on Friday. Or